Hello again. Let's come back to our learning targets here for the second part of this lesson. What we just finished was we just finished a lesson in which we use cosine and sine functions to resolve a vector into its horizontal and vertical components. Now in part two, we're going to go in the opposite direction, because sometimes in physics problems, you know what the x and the y components of the vector are, and you want to put them back together to find the overall magnitude and direction of the original vector. So that would be like taking the sides of a triangle and working backwards to find the length of the hypotenuse and the angle that the hypotenuse makes. So let me show you how to do that. The question is what if the x and y components of a vector are known and you want to find the magnitude and the direction, meaning the angle, of the original vector? So let's take the example that we had used earlier. Let's pretend that we just know that we have a vector where the x piece is equal to 8 meters per second and the y piece is equal to 6 meters per second, and we want to find out what is the overall magnitude of the vector and what is the angle that it makes with respect to horizontal. So I hope that you are, again, recognizing that there's really a right triangle which is embedded in this picture. In fact, there are two, but we're going to use probably just one of them. And what we're going to do is use the Pythagorean theorem to find the diagonal, and then we're finally going to use that tangent function to get the angle. So let's talk about the magnitude piece. The Pythagorean theorem is a very famous theorem in mathematics. It says that a squared plus b squared is equal to c squared. Of course, if you put this in physics terms, we're going to say that v squared is going to be the hypotenuse squared, and that's equal to the sum of the squares of the two component vectors. So vx squared plus vy squared. So our unknown here is v, so we could write v squared is equal to, and then we supply the two component vectors, 8 squared plus 6 squared. Of course, that's 64 plus 36. And 64 plus 36 add to 100. The square root of 100, don't forget, is going to be equal to 10 meters per second. That's how you get the magnitude of the resultant. Okay, so it's that easy. You really just take those two components, you Pythag them. I like to use that as a verb. And then you take the square root to find the magnitude. Okay. Now, how about that angle? How do we get that? This is where we finally get to use the inverse tangent function. Fun. And again, you need to make sure that your calculator is in degrees, because we want to get that angle in degrees at the end of the day. So we're going to end up using the inverse tangent, but let me just show you how that's going to work. If you recall from SOHCAHTOA, the tangent of theta is equal to opposite over adjacent. So in our physics picture, the tangent of theta is equal to Vy divided by Vx. And so you really have to go back to that picture and look at how the angle is labeled. It's right there. So how do you solve for theta when you have tan theta is equal to something? Well, that's where you do the inverse tangent. And the argument of the inverse tangent becomes this ratio of Vy divided by Vx. So on your calculators, what you do is you probably have to hit the second button and then tangent to make it inverse. And then in parentheses, you would put Vy divided by Vx, which in this case would be 6 divided by 8. And you can try that right now. So if you take the inverse tangent of 6/8, or 0.75, you should get a 37-degree angle. And remember, that was the angle that we assumed in the first part of this. So there you have it. We actually do need to use all three of the trig functions, sine, cosine, and tangent. We use sine and cosine when we resolve a vector into components, and we use the tangent when we're trying to find the angle of the vector when we know its components. Now, one word I want to also mention here, a little bit of vocabulary, is the word resultant. You should know what that means. The original vector that you obtain by combining the components is called the resultant of those components. And this is the first time I've really used that word, but I'm going to use it again, and you're going to come across it in things that you read. The word resultant means a sum, and in vector speak, we talk about the resultant vector as being the sum of two vectors. So really, if you think about the two red vectors that are shown here, the x component and the y component, what we're really doing when we find the diagonal, when we find its size and its angle, is that we're really adding those vectors together in a vector way to find the resultant. And the way that we did that was we used the Pythagorean theorem and the inverse tangent. So this is like the very, very first step in vector math. And you can go a lot farther than this. But I think at this point in this class, it's really important that you know that if you have two vectors that make a right angle with each other, that the way that you find their sum or their resultant is to basically do what we said, use the Pythagorean theorem and use the inverse tangent to find that angle. And that will give you, the magnitude and the direction for the resultant. So let's review the first two lessons here, okay? Number one, vectors have components. The components are the part of the vector that align with the x and the y directions. To resolve the vector into its components, you have to use the cosine and the sine functions. Alternatively, if the components are known, you can reconstruct the parent vector, called the resultant, by combining the components via the Pythagorean theorem, which gives the magnitude, and the inverse tangent function, which gives the direction. And I don't know what that word "the" is there for. So hopefully, this is not news to you in terms of the mathematics of this. But what we want to do next in the last part of this lesson is apply this mathematics to physics, because the idea here is not to teach you math, but to show you that math can be used to make important predictions and to quantify our understanding of projectile motion. Okay, so part 3 is coming up.